Right, good evening, everybody. I can assure you, you are in for an absolute treat. I've seen a preview of this, and it is quite remarkable. I am Tim Littlewood, the Director of Science here at the Natural History Museum, and I'm delighted to welcome you all to the very first edition of our Dig Deeper series, analysing asteroids from Bennu back to base. This talk also forms the launch of Sir Brian May and Professor Dante Lauretta's latest collaboration, Bennu 3D, Anatomy of an Asteroid, published by the London Stereoscopic Company. For those of you in attendance and on site this evening, there will be the option to buy a signed copy after the talk. So one of the biggest questions asked of humanity is, where did we come from? Over recent decades of dedicated research, asteroids have become incredibly important in understanding how early life evolved on Earth. You'll come to learn that during the course of the evening, Bennu is a time capsule, approximately half a kilometre wide. It's a carbon-rich time capsule containing information from the dawn of our solar system some 4.5 billion years ago. However, it's also perhaps one of the most hazardous asteroids in the solar system, with a chance of impacting Earth in the year 2182, for any youngsters in the room, drastically influencing the future of both people and the planet. Bennu 3D, Anatomy of an Asteroid, is the world's first complete and stereoscopic atlas of an asteroid. The book follows the story of Bennu's exploration through mission data and stereoscopic images, allowing us the impossible feat of seeing Bennu's rugged and rough landscape in glorious 3D. Yes, you can believe the hype. It's all true. And of course, what better time to release this book than now, just weeks before OSIRIS-REx, the first American mission to deliver an asteroid sampled back to Earth, drops its treasured cache down into the Utah desert. Joining the team in the USA will be one of tonight's panelists, Professor Sara Russell. Sara will be among the very first to lay eyes on this specimen to assist with preliminary observations and interpretations on the sample before bringing it back to the museum, where it will be further studied in our state-of-the-art analytical facilities by our team of meteoriticists, mineral scientists, technical experts, and students. There's a test for those with a sibilant S. You'll meet many of this team this evening as they wander around the talk after the talk with some examples from our world-class meteorite collection. Our planetary sciences group work on many aspects of our solar system, from the origin of water billions of years ago to landslips that happened on the moon over the last few years. Please ask them about their research. It is indeed fascinating. Our team will investigate the mineralogy, chemical composition, and water content of the sample to unpick the geological history of Bennu, discover what it can tell us about the birth of the solar system, and to understand further the role of asteroids in the origin of life on Earth. The museum is a world-leading science and research centre working at the forefront of planetary science, including a collection of over 5,000 space rocks spanning 4.57 billion years of our solar system. It's always amusing when kids say, the oldest thing in your museum must be a dinosaur. And then you point at a meteorite and you go, nope, it's that thing over there. He said, I do like dinosaurs, but not that much. So the NHM is one of the best institutions in the world to research space and find answers to some of the biggest questions asked of humanity. Where did we come from? With this in mind, who better to host such a fascinating conversation than the BBC's long-running presenter for the renowned Sky at Night programme, Professor Chris Lintott. Chris is a professor of astrophysics at the University of Oxford, and I'm pleased to announce that from September will also be the 39th Professor of Astronomy at Gresham College. His own research includes studying interstellar asteroids and understanding galaxies. Bit of housekeeping for those in attendance on site before I hand you over to the main event. I'd like to ask you all to make sure you have a pair of glasses to hand, which you'll be needing for the lecture. Please let a member of staff in the room know if they have them or not. I noticed people were walking in, some were being sort of inadvertently bumped to the floor, so make sure you've got a pair of these because these make all the difference. And without further ado, please welcome Professor Chris Lintott, who will introduce our panel of speakers this evening. Chris.
Thanks. Thank you. Thank you very much for being here. Thank you for joining us online. My role is basically to get out the way as quickly as possible because I've seen what you're in for this evening and it's a treat. The images in this new book, the images we're going to see on screen, the images you're going to see at home on your computer screens are truly stunning. And they're a reminder that as we go out into the solar system, as we undertake this great voyage of humanity to explore our surroundings, one thing we're really doing is taking what are points of light in the sky and turning them into worlds that we can explore. And I think that's what OSIRIS-REx and our panelists this evening have done for me. They've turned Bennu into a place that I'm eager to see more of. And that's all the more true when geologists can get samples back down to Earth, which makes tonight's discussion incredibly timely with the return of samples due in September. So at this point, please welcome onto the stage tonight's panel. So let me introduce them. I will start, I think, let's start in the middle. Sir Brian May is perhaps best known as a world expert on the zodiacal light, the dust that fills our solar system. I mean, he is in my world. Anyway, he did his PhD on this topic just next door at Imperial College, admittedly interrupted by a music career that I need not tell you anything about as the guitarist for Queen. What perhaps you don't know is that Brian's also an expert, a collector, and a true scholar in the field of three-dimensional photography, both historical and taking us into the space age, which is how he ended up as a member, a bona fide contributing member of the OSIRIS-REx team. He's also the founder of the modern London Stereoscopic company, publishers of Bennu 3D, Anatomy of an Asteroid, which I may have mentioned, and the only publisher in the world dedicated to publishing stereoscopic work. So please welcome Brian. Thank you very much. On his right is Professor Dante Lauretta, a Regents Professor of Planetary Science and Cosmochemistry at the Lunar and Planetary Laboratory at the University of Arizona. He's the principal investigator for the OSIRIS-REx mission, which for those not in the know means he's the boss. He's in charge and has guided this mission from an idea to its successful visit to Bennu. He's an expert in near-Earth asteroid formation, evolution. We've just been talking about quantum computing, which we probably won't hear much more about. But please welcome Dante to the stage. I know many of you are here because you're supporters and friends and fans of this marvelous museum, and so we couldn't have this event without asking our very own Professor Sara Russell to join the panel. She's the leader of this place's Dynamic Planetary Materials Group. Dynamic Planetary Materials? Dynamic Planetary Materials Group? Both, I think. And a member of the OSIRIS-REx science team who's been working with Dante for over 10 years. And she's going to start our evening by introducing us to the science of asteroids. Sarah.
Thank you. Thank you very much, Chris, and welcome everybody. I'm so excited to welcome everybody here, both in the room and online, to this talk, which I'm really looking forward to hearing what these guys are going to say. It's been such a thrill for me to be involved in this amazing mission that we're going to learn more about, and a thrill to be able to tell you more about this amazing new book. And one of the things I really love about this book is it starts right at the beginning of the history of meteoritics and asteroid science. And that's something that our institution has actually had quite a lot to do with. So we got our first meteorite. Oh, there we go. We got our first meteorite over 250 years ago in 1776, and that was Krasnojarsk, a Russian meteorite. And at that time, we didn't even know what meteorites were. So now we know that a meteorite is any natural extraterrestrial object that falls down to space. In 1776, it was just a weird-looking rock. It wasn't until a few decades later when in 1795 the Wold Cottage meteorite fell in Yorkshire in the north of England that was seen by several people and was widely written about and analysed, that we started to realise that actually we do have this amazing treasure on Earth, which is that we have these space rocks for us to analyse and to learn about our solar system. So since then, we've learnt a lot about meteorites. So there are about 70,000 known meteorites in our collections now. We know that nearly all of them come from asteroids. A few of them come from Mars, and a few of them come from the Moon. But our asteroidal meteorites are ones that can tell us about the formation of our solar system, because we know asteroids formed 4.5 billion years ago at the time when our solar system was just beginning to form and planets were first beginning to emerge. So we've been looking at meteorites this whole time. We've learned so much about them. And I'm going to take you from the very first recovered UK meteorite fall to the most recent one. So on the left here is a dirty splat in a driveway that appeared overnight in a driveway in Winchcombe in Gloucestershire in February 2021. And this turned out to be the most recent UK meteorite fall, an amazing sample. So it was collected really quickly within 12 hours of its fall, so we managed to get an uncontaminated sample of it, and we put it straight into our laboratories here at the museum, which are just underneath our feet. These are on the right, so just some examples of the kind of work that we do here. So the top image is a crumb of the meteorite that's been put in the electron microscope, and the elements have been scanned. So this contains abundant calcium, which is the greenish looking stuff, which is a carbonate formed in water. And then the bluish material that it's lying on top of is a clay mineral, also full of water. So that tells us meteorites like this have lots of water in them, which might have seeded water in the early Earth. Then the bottom image is a blob of carbonaceous material. It's actually a very complicated organic material, organic carbon-rich, nitrogen-rich, and oxygen-rich material. And we think that objects like this inside meteorites may have seeded the Earth with the ingredients needed for life. So we can learn an awful lot about meteorites, about our own origins. But one problem with studying meteorites is that we often don't know where they came from. And we can't know what the geological context of the object it came from was. So we can't look at all the rocks around it and how they relate to each other. So for that kind of work, we really need space missions like OSIRIS-REx that Dante is now going to tell us a little bit about. Thank you.
Thank you, Sarah. It's great to be here at the Natural History Museum. I know myself and many others in the field consider this one of the spiritual homes of meteoritics and cosmochemistry, so it always thrills me. We've been doing interviews in the meteorite collection, and you can just feel the ancient rocks all around you. And a lot of people ask me, why do you study rocks? What's so interesting about them? Well, they tell me their stories. They tell me their history, and that's what we unravel when we do the detailed chemical analyses like Sarah just showed us. But before I begin, I have the privilege of being on stage with my co-author, Sir Brian. But like everything on OSIRIS-REx, this is a team effort, and several of the authors are here with us tonight. If you wouldn't mind standing up, maybe turn around since you're in the front row tonight. Turn around, take a bow. We have Karina. Karina is our image processing engineer. All of the amazing maps and images that you see in the book, she was the one that took incredible care to make sure that they were put together just right. The lighting conditions were corrected for. Really amazing. Here we have Ken Coles. Ken is a planetary cartographer and known primarily to me originally as the lead author of the Atlas of Mars. He reached out asking if he could come and do a sabbatical at the University of Arizona. Were there any projects? And I was like, well, we're working on an atlas of an asteroid, right? So sounds like the perfect project. And he really brought a great perspective and a lot of discipline to the project and all of the knowledge from publishing high-precision cartography in the Atlas of Mars. And Kat Wollner, who is the chief editor for the OSIRIS-REx project, I think is the only other person on Earth besides myself that has read every paper that we published on the project, deep knowledge of asteroid Bennu, as well as the rigors of scientific publishing. So thank you for being here tonight and for all of your help on the project. So what is OSIRIS-REx, right? OSIRIS-REx is many things, but I think to me personally, first and foremost, it's just an awesome acronym, right? That describes the principal scientific objectives of the mission. It's a NASA mission in the New Frontiers program to go out to a near-Earth asteroid named Bennu, map it, select a sample in the universe. How did Earth come to be a habitable planet? Why did the origin of life occur here? And is it likely to have occurred elsewhere in our solar system, or in our galaxy, or the broader universe? We have other research investigations. We look at the spectroscopy, how it reflects sunlight. We'll be able to ground truth our inferences of the mineralogy and chemistry on the surface. Resources, we look at asteroids, especially near-Earth objects, as potential economic development to further human exploration and robotic exploration of deep space. Security, I'll tell you more about this tonight. You know, when you go to a near-Earth asteroid that you can easily reach, get a sample and return, it has a reasonable chance of coming to you at some point in the future in a very bad way. So it's one of the most devastating natural disasters facing our planet, and really, I think, the only one that we have a chance of doing anything about. So it's a small insurance policy to understand this asteroid hazard and develop techniques and technologies for the future in the case that they have to deal with it. And we're the regolith explorer. Regolith is the loose blanket of rocks and gravel that cover these airless bodies, and we are an explorer. It's truly a scientific expedition. I think the star of the show, actually, is the OSIRIS-REx spacecraft. It was amazing to see this go from early concept stages, literally drawing on a cocktail napkin, PowerPoint presentations, I don't know how many thousands of PowerPoint presentations, to ultimately seeing this amazing robotic solar system explorer spring to life, come into action, come into being. And on September 8th of 2016, we put it on top of the amazing Atlas V rocket and launched it on its journey to asteroid Bennu and back. So here is the asteroid, the target of our mission, the subject of our book. It's about 500 meters in diameter, so I think of it as a small mountain in space. It has an amazing, in fact, an astonishing shape. We didn't really appreciate this structure until we started exploration of near-Earth asteroids, both with the OSIRIS-REx mission and our partner mission with the Japanese Aerospace Exploration Agency, Hayabusa 2, which Brian will show you the target of theirs. And you'll see a very similar kind of structure. It's almost a sphere, which is unusual for something this small, but it bulges at the equator. You can see it's pockmarked by impact craters where other asteroids have struck it, and it's got these big boulders like warts hanging off its edge. Over there on the left, you can see its orbit. The orbit of the Earth is in green. The orbit of the asteroid is in blue, and the sun is at the center. And you can see from this diagram that, in fact, Bennu appears like it could get very, very close to the Earth. Let's put this into action. I'm going to flash forward. One of the things we did on OSIRIS-REx was measure with exquisite precision the orbit of this asteroid. We know the orbit of Bennu better than any object in the solar system, even better than the Earth, which is always astonishing to me. But despite that unprecedented knowledge, there's still some uncertainty. And that's because we can only predict with that level of knowledge where Bennu is going to be up until September of the year 2135, which, you know, that's not that far away. And Bennu is going to come in between the Earth and the Moon during that encounter. And that's where the uncertainty in our knowledge kind of blows up, because we don't know how the Earth's gravitational field is going to perturb the orbit of the asteroid. So what we do is we launch a fleet of virtual asteroids that cover the entire uncertainty range of all of our knowledge, and we propagate that out into the future. And when we do that, we flash forward to the year 2135. Here we go. And you see, here's just two of those possible scenarios. The first one, Bennu's coming back to the Earth, and it's on an impact trajectory. So you can see right there, September 24th, 2182, if you want to put it in your calendar book. Bennu, if the odds line up and we don't do anything to prevent it, will impact the Earth with an energy of over 1,300 megatons, which is 3 times more than all of the energy ever detonated in nuclear weapons in the entire history of humanity. That's about a 0.05% chance. And I like to say, you'd cross the street with those odds, right? That's pretty far out there. But considering the level of devastation that would result, it would be a major natural disaster. If it hit a city, it would wipe out something the size of London, for example. Most of our virtual impactors miss the Earth, and Bennu goes on to continue this cosmic ballet with our planet with repeated chances and close encounters off into the future. So we have a lot of reasons that we want to study it. Again, the origins investigation, asteroids as the bringer of the seeds of life, right? Do they contain carbon-bearing molecules of the kinds that make up biochemistry, the amino acids that make up all the proteins of all life on Earth, the nucleobases, which make up the DNA and RNA in our bodies, the sugars, the lipids that make our cell membranes, etc. So I won't go into too much detail here because Brian's got a great set of data to show us about the arduous process that we went through to find the site on the asteroid. But I can tell you, we were in real trouble when we first saw Bennu arise. You take a look at the surface of this object. It is not what we expected from our ground-based astronomical campaign. We thought it was going to look like a beach. I even said that many times. I got up in front of my team. I got up in front of NASA. I even probably got up in front of God and said, this is going to be a smooth surface. It's going to be easy. It's going to be easy. It was not an easy process to find the sample site. But at the end of the day, thanks to the enormous effort of the team, including the critical role of Brian and his collaborator, Claudia Manzoni, we ended up selecting a location called Nightingale. And you can take a look at it here in a mono image. It's really hard to get a sense of the topography of what you're looking at, but I want you to remember this mono version of our sample site, and then you'll see in 3D the real challenge that we faced here. Why did we pick Nightingale? Well, it's in an impact crater, a recent crater. It looks really young and fresh. Just from its structure here, you can see the center of the crater where the green box is, which is what our final target location was, much, much smoother than the surrounding rocky terrain, which kind of dominates the average surface of Bennu. It was red. Bennu is a blue asteroid. We say it's a B-type asteroid. Why it's blue is actually one of our mysteries. We're hoping to unravel that when the samples are back on Earth. But we think it gets red when there's high concentrations of organic molecules and also fine-grained particles. So the combination of those two, both of the key targets of the mission. It's in the northern hemisphere, about 56 degrees north, which means it stays relatively cool compared to the equator, where it gets hot and cold. Bennu rotates every 4.3 hours with over 200 degree Fahrenheit temperature swing. And that can damage the materials that we're interested in and modify them. So we really are trying to get that pristine, freshest material we possibly could. Also, at the end of the day, it wasn't the safest place, and we had a long debate between science and engineering on whether we should go here or to a backup sample site we called Osprey. And it came down, I had to make that call, and I said, I'm going with the science. We didn't come all the way out here to be timid, right? Let's get to Nightingale, let's get that sample and get home. It's got the fine particles, it's got not only the organic molecules, but we see water. And you might think, wow, water on this tiny asteroid, how is that possible? It's not liquid water, it's not ice. It's water locked up inside minerals called clays or phyllosilicates, which are stable at much higher temperatures than solid ice or liquid water is. And that's exciting too, because not only are we interested in the delivery of the organics for our biology, but we're interested in the water that's in our oceans, as well as the air that's in our atmosphere. All of these things that come together to make Earth a habitable world. So I mentioned that we were really surprised by the surface of Bennu, and I love to show this next animation because this we created before we even arrived at Bennu. And this is what we thought the sampling was going to be like. So here, let's try that again. I have a green screen on my laptop here. Look back to Nightingale. Let's try it one more time. There it goes. Just like spaceflight, anomalies pop up and you got to deal with them. One more time. Here we go. Coming down about 10 centimeters per second. This is about a 30 centimeter diameter, basically an air filter. I like to say it would look right at home on the carburetor of a 57 Chevy. It's basically leaf blower strategy. We have some bottles of high purity gas. We expected that the sample head would sit firmly on the surface of the asteroid, a nice solid surface. We were thinking this is a rocky body. You should be able to just touch down, quickly grab your sample, and back away with that scientific treasure in hand. Well, let's take a look at what really happened. So here we're looking at views from the SAMCAM, our sampling camera that documents sample collection. It's 2 images taken about 1 second apart, right before contact and right after contact. And I'll never forget this moment. You know, we sampled around 3 o'clock in the afternoon. I was in Denver at the Spacecraft Control Center. We didn't get these images for about another 12 hours later. And so I had to stay up, right, waiting for the data to trickle back down from the spacecraft. I saw the first one. I was like, okay, that looks good. We're on the surface. And then I saw the second one, and I was like, I know we got the sample right away, because the sample, the surface is fully compliant. There's no resistance to our downward motion. We're just sinking in, and you can see disturbances like this rock right up here. It's kind of rocking as a result of the contact, even though it's about 30 centimeters away from the contact point. And then this one down here, it's acting like a seesaw. The sampler's barely touching the edge of the rock, and it's flipping up here, and all of these dust particles are getting lofted off the surface. And then my favorite one is right around here, about 9 o'clock on the TAGSAM head. This was a boulder that we struck right in the middle. It actually extends into and under the head, and it just completely fragments and shatters upon contact. So that means the surface in this case was really soft and crushable and friable. So I was like, great. Now let's see what the next image looks like. What happened after we fired that gas? And man, the first thing I noticed was TAGSAM's going into shadow. And that means it's digging down. It's not stopping. There's no hard surface here. In fact, it's like hitting a ball pit at a child's playground. We were just plunging down at that initial contact of 10 centimeters per second. And then you can see it looks like a snowstorm, right? That goes from much larger particles. You can see a giant rock right there fly in front of us. Kind of a camera killer if it ended up hitting one of our optical elements. And then right about now, it's going to get really fine grained like this blizzard, which is great, right? Because that means a lot of small dust and particles are getting inside that TAGSAM. To give you another view, here's a second camera. And I know Brian loves this because these two were almost at perfect angles for making stereos. Here's the shadow at TAGSAM, a cloud of dust, and then you can just see the surface erupt and explode. And a giant impact crater is being dug out as a result of blowing the gas down. Nothing like this ever happened during the testing in our laboratories or on the microgravity aircraft. And if you watch the upper right here, you can see some giant rocks, meter-scale particles. They're tumbling, some of them very plate-like this one right here. And then the asteroid surface shows up here, and you can see these shadows of boulders that are flying off away from the sampling site, which is down to the lower left edge. And right in this region here, this large boulder gets collided with and crashed into an enormous dynamic event, way beyond anything we ever anticipated. So, of course, I had to go back to the computer animators and say, well, we need to show what really happened when we made contact with Bennu. So we're coming in 10 centimeters per second, and we just sink down into that asteroid surface. We fire the gas, and we just blow the surface away from us. We ended up making a crater over 8 meters in diameter. The biggest divot we ever dug in all of our laboratory testing was about 20 centimeters across, right? The other thing is, just look at what we did to this beautiful billion-dollar spacecraft, right? We just buried it in the asteroid. And here with those bright lines, that's the rocket engines firing. It took 9 seconds to stop the downward motion, and that's 17 seconds to back away from the surface. We only planned on staying in contact for 5 seconds. We went about 50 centimeters down into the subsurface of the asteroid, and I honestly believe if we had not fired those rocket engines, it would have just disappeared like into a pool of quicksand. So you would think, okay, Bennu's been messing with their minds for a couple years now. Hopefully everything is going to go according to plan from here. Nope. So 2 days later, on October 22nd of 2020, we brought the sample head in front of that SAMCAM. Now we're looking at the bottom of it. And the first thing I see is that we're bleeding. There's particles that are just flowing away, being lost into space, becoming part of the interplanetary dust population at this point. And I'm thinking to myself, every one of these particles is somebody's PhD thesis. Never be written. lost to space, and I was like, we got to stop the bleeding. I called an immediate halt to all spacecraft motion, no rocket engine firings, no movement of the arm, no movement of the solar arrays. We could see the particles going past a different set of cameras called star trackers, and at least I knew as soon as we stopped all motion, the particle loss stopped, and we rallied the team, as always, and we safely got the TAG-SAM head stowed into this amazing sample return capsule, which is coming back to Earth on September 24th of this year. And the requirement, what we sold to NASA was we would bring back 60 grams of sample, even with the material that we lost, which was well over 60 grams, by the way. We lost more than the whole mission requirement. We still think there's probably about 250 grams, although we have 101 gram uncertainty on that. That's a treasure for scientific analysis. We're very excited. We got that dust particles. The reason we were bleeding is because there was a 3-centimeter stone that was jammed, and it jammed open the flap that was supposed to keep the sample secure inside there. That's probably because we had so much material. It was kind of like a bucket of water that's filled right to the top, and you got to carry it up the hill, right? Any tiny motion is going to cause slosh and material to escape. We think we got those clay minerals, we got organic molecules, we have different carbon minerals called carbonates, which you're probably familiar with as the white crusty salts around your taps. Other minerals that form in hydrothermal systems like iron oxides and iron sulfides. And when you look at this asteroid, and I want you to pay attention when Brian's showing you the beautiful stereos, there's an enormous diversity of rock types on the surface. Some we think are like our meteorites, the carbonaceous chondrites that we've been studying our careers to try to understand the origin and history of the solar system. But we also see tiny bits of volcanic rocks that look like they come from a famous asteroid called Vesta, one of the very first asteroids that were ever discovered. As you saw from that contact where that sample got crushed, some of this stuff is really fragile and wouldn't make it through the Earth's atmosphere. That's really exciting for Sarah and I, things we've never seen before from outer space. You never know what you're going to get. Hydrothermal mineral deposits, those carbonates show up in giant veins over 1 meter long and 10 centimeters thick. That means you had to have water flowing, not through Bennu, but through a much larger asteroid, probably 100 kilometers in diameter in the main asteroid belt. Radioactive elements melted ice and drove hydrothermal systems. And Bennu is just a tiny fragment of that object, which was probably shattered in a catastrophic collision in the main asteroid belt, maybe 800 million to 1 billion years ago. And we saw Bennu was very active. It was shooting bullets off into space. Particles were flying around. It looked like popcorn, constantly ejecting material, which was re-impacting the surface. Caused quite a stir when we first saw it. Eventually, we realized it probably wasn't a hazard to the spacecraft, and now it's just a cool science experiment, and we're hoping those are in the sample as well. But you never know, right? Until this treasure is safely in our laboratories at NASA's Johnson Space Center. And I invite everybody to watch. We'll have a NASA live broadcast on September 24th of this year, I think 3 p.m. local on NASA TV. We're going to release that capsule, where it's going to hit the top of the atmosphere, 27,000 miles per hour, about 12.4 kilometers per second. The heat shield will get up over 5,000 degrees Fahrenheit. Most of that speed and velocity will be shed through frictional interaction with the atmosphere. Once it reaches free fall, parachutes will open, and it'll gently glide down to the Utah desert, where me and members of my team will be waiting in a series of helicopters to recover it, quickly get it onto a U.S. Air Force jet, and fly it to the NASA Johnson Space Center, where we'll be distributing it to laboratories around the world, including those right here, as Sarah said, underneath our feet at the Natural History Museum. So that's a whirlwind tour of the OSIRIS-REx mission. But what we're here to talk about tonight is this amazing collaboration and this beautiful book that we have produced, and the story of how Brian and I got to be collaborators. And I got an email shortly after we launched in 2016 from Dr. Brian May. And I thought, oh, this has got to be a joke. Some of my friends are having a laugh. Everybody knew I was a huge fan, and I was like, okay. He's like, congratulations, we're really excited. And I was like, oh, actually, finally realized I was actually talking to Brian. And I was like, cool, I can just at least tell my kids I wrote email with a rock star. And then we started putting some of the images out on the internet, and I got another message in 2018, and he's like, hey, Claudia and I found some of your images. We put together a stereo. And he sent me a stereo viewer, one of his owl viewers, and I looked at it, and it was like, literally, a new dimension opened up. And at that point, we were really starting to grapple with the rugged reality of the asteroid, and the team was freaking out a little bit, right? It's like, okay, what are we going to do? How are we going to solve this? It was a while before we were going to get any kind of good 3D data from our laser altimeter. And Brian and Claudia, I said, are you guys serious? You really want to help? And he's like, absolutely. He says, I love to be part of creative teams. Put me to work. And I said, you got it. And I started sending him coordinate after coordinate, I think over 50 sites. We were like casting about desperately for anywhere that we might be able to sample. And they started coming in, and it was like, nope, nope, nope. And I was like, maybe, right? Okay, maybe. And so we whittled them down to the story that Brian's going to tell. It was a critical contribution to the program, lifted everybody's spirits, helped us overcome the challenge. And I'm going to turn it over to Brian to guide us through the amazing data collection of stereos from asteroid Bennu.
Oh boy. I've got to say thank you to Dante, who always gives me a great big up before I walk on here. I have to tell you, he's a very hard act to follow, you know, if we're talking about shows. But he's become a great friend throughout this process, and I feel incredibly privileged to be here as part of this team who achieved this incredible result. And of course, I have to say, you know, Dante, as you've seen, is the real rock star here. So I'm just the icing on the cake here. But I'd like to tell you a little bit about stereo and how this happened, and how stereo happened, basically. And I'm just wondering, this would be a good time to put these things on, okay? You okay with that? Anybody not got any? So this is what we could be showing you, and I like to say, you know, this could be a cave painting, really. It's a very beautiful result from a very beautiful expedition, but it's still something which is flat, sitting on a wall. I wonder if I can work this thing. But what we're offering is this. Ooh. So I've got a little bit of an ooh there, and this is what I enjoy getting. And also, of course, we can offer this. So that kind of answers the question, I suppose, I'm hoping, you know, why stereo? Why stereo? Because it gives you a much better instinctive feel for what an object is like. And I like to watch this for a little while, just to see the thing go around. If you're okay with that, because this is partly about pretty pictures and how we experience the world through our eyes. It wasn't always that way. Going back to cave paintings, it's something on a flat wall, and it was very good for those guys to capture what they saw around them in their surroundings and keep it in their house. And we have the same kind of instinct, don't we? We go around with our iPhones and we try to capture things, and we take them into our houses and keep them with us to sort of treasure those memories. But mainly they're flat. And they were flat all the way through the Renaissance, even though people like Leonardo da Vinci discovered the rules of geometry and perspective. What they didn't discover was the fact that we have two eyes for a very good reason in evolutionary terms. Having two eyes hasn't just given us twice as much information, it gives us kind of thousands of times more information, because it gives us a proper perspective on the universe around us. Obviously very advantageous if we're trying to avoid predators or if we're trying to find the next meal. So the world was flat, or at least the world of reproductive representational art was flat until 1852, when this gentleman, we'll have to say goodbye to this for a minute, okay? I'm going to show you this gentleman, and he is another star of our show, really. He is Charles Wheatstone, who in 1852 figured the thing out. And he changed the world in a very modest way. But what he discovered was that we have two eyes, which give us two different views of the universe every moment of our lives. We have the left eye, which gives us this view here. We have a right view, which has the same view, but from a different viewpoint. What we have to do to make representational art, which is in depth, is give the left-hand picture to the left eye only, and the right picture to the right eye only. He called this stereopsis, and he invented a machine to do just that, which he called a stereoscope. And that's how we got 3D into our lives. That's why we got Avatar. That's why we got Mighty Mouse when I was a kid, red and green spectacles. It's all the same thing. So I'm going to take you a little bit on Earth just for a moment. Here's a normal scene, captured quite nicely in colour, a scene that we might see of the forest outside our door if we're so lucky, if we still have any forest around us. And that's the flat thing. Again, that's what the cavemen could have put on their walls. What Charles Wheatstone did was say, okay, I want to photograph from this. This is before photography was invented, strangely enough, but nevertheless, Charles Wheatstone said, give me a picture for the left eye taken from one particular viewpoint. Then let's move a little way to the right and take another picture from another viewpoint. And what we will do is we will present the left picture to the left eye and the right picture to the right eye. And this is what we get. I'm getting a little ooh. Mm-hmm. This is actually slightly exaggerated because what we've done here is not move the 2.5 inches between our eyes, but a little bit more. I've moved about a foot here, which gives you an enhanced stereo view. And that's what our astro stereo is all about. We try to find two viewpoints which are far enough apart to give us some good parallax, some good stereo detail in what we're looking at. Just before we move off planet Earth, I want to show you this to illustrate the fact that sometimes stereo will give us insights which we cannot get without the 3D view. Very hard to figure out what this is, right? Left view, right view, but the stereo view gives us this. So it's immediately obvious what the actual shape of the thing is that we're looking at. And if we don't have our stereo vision, we're severely handicapped. So going into space now, because I've kept you on Earth long enough, here's a comet. And I have to, at this point, give credit to my wonderful collaborator, Claudia Mansoni, who can't be with us tonight, but I'd still like to give her a round of applause if you don't mind, because Claudia and myself work as a team, and what she does is plow through all the data, all the archives that are part of the space missions. So we've been doing this quite a long time. This is the Rosetta mission to a comet called 67P. And here again, we've managed to secure a left-hand view, if you like. Claudia was able to find a right-hand view from a different part of the mission. And again, we give the separate pictures to our separate eyes, and this is what we get. I got a whoa there, which is very good. I like that. So it's a little bit of a strain on the eyes, this, because we've actually probably gone a little bit too hyper, as we call it. The baseline is perhaps a little bit too far apart, but nevertheless, it gives us a real insight into what the thing looks like, the difference between that and that. So we've been trawling NASA websites for quite a long time, but I had the opportunity to actually work with Dante. Oh, just before we leave the comet, this is a view which I think also illustrates the value of 3D. We're sitting here inside the tail of that comet 67P, looking back up to the nucleus. And I think you can actually feel this tail all around us. Mm-hmm. Stereo gives us a very great feeling of actually being there. Of course, all the missions to the stars, to the solar system at the moment are unmanned. We don't actually get the opportunity to sit out there and see these things. But because, for instance, OSIRIS-REx's cameras are so good and so well worked, and because of the extra dimension of stereoscopy, we get to feel like we're there. And probably worth mentioning at this point, there are no stereo cameras on OSIRIS-REx mission. It wasn't part of the plan. So we have been complete opportunists in this way, in finding ways of making stereo pictures. Okay, I'm being very indulgent here. I had a hand in the New Horizons mission to Pluto, and Pluto was a white dot when I was a kid. Just before they did the flyby, this is what it looked like. We had this, I happened to be in the control room, an immense privilege. We got a left-hand view. At the actual moment of flyby, this is the picture we got. Put the two together, and you have the first stereoscopic picture of, I call it a planet. Do you call it a planet? I don't know, is it getting into controversy here. The dwarf planet Pluto, okay? And here she is with her sister, Sharon, because it's a binary system. Okay, enough of this. Asteroids. The book this beautiful book here, which I just might remind you what it looks like. Exceptionally beautiful book. What it has is a lot of history. In fact, it has the complete history as detailed by Dante and all of us working on this tome, which gives you the history that humanity has in its relationship with asteroids. Claudia and I had already been out there looking for our stereo data, if you like, and this is the asteroid Ceres, and that white blob was very enigmatic for a long time, but Ceres was the first asteroid discovered. I think that's right, isn't it, Dante?
That's right. Asteroid number one.
I'll ask Dante to interject as we go along,
Bet.
because he knows more about this than I do. This is Ceres. The second one is Vesta. Again, one of the very early asteroids detected by humankind. A very interesting object, and interesting, of course, because it's still very solid, and I think until recently, most of the asteroid explorers expected asteroids to look like this. All the artists' impressions of what we're going to see when we get there looked something like this. Solid bodies, a little bit like the moon, where you get well-defined craters. And of course, with Bennu, it was nothing like this. And I think that's one of the joys of unmanned space exploration. You never know what you're going to see until you get there.
And we might have fragments of Vesta on Bennu. If you go back to that real quick, Brian, there's a giant impact basin in the southern hemisphere. It almost looks like just a plain. And we can actually trace fragments from that impact and estimate where they might have crossed Bennu's orbit as it wandered through the solar system. So we're excited we might be bringing back pieces of this asteroid too.
Amazing bonus. Here we are, and this is Itokawa. Itokawa was visited by the Japanese JAXA mission, Hayabusa 1, and again it looks fairly solid. It looks like it might have a sort of peppering of boulder type material on it, but you would expect to find a nice place to land without too much trouble.
This is where we got the idea that Bennu might have the beach. If you look at what we call the neck there's that smooth region of Itokawa. And I told the team, if we can sample Itokawa, we can definitely sample Bennu's. Bennu's going to be easier than this one. So this kind of fooled us.
Some hopes. And this is the Hayabusa 2 mission, JAXA, their second voyage to asteroids. And this object is called Ryugu, and kind of a sister object to Bennu. Would you say that's correct?
That's right, yeah. They have similar maybe compositions and orbits, and they may be fragments from the same catastrophic disruption that shattered that giant asteroid hundreds of millions of years ago.
Yeah, this is one of the objects which gave rise to the new term rubble pile, which in the beginning I thought was a term of abuse, but actually it turns out to be the new technical term for this kind of body. Very similar body to Bennu. And I can see landing on that must have been quite tricky as well, although we weren't involved in that. We kind of did this from the outside. Claudia and I got to know the Hayabusa people a little after this. But then we come to Bennu, where we're able to lead an active role. Now, what happens in Bennu? It ought to be simple, right? I mean, again, you don't know quite what to expect. But here's a strange rock on the surface of Bennu, which I'm plunging straight into. Called Gargoyle, we call it Gargoyle. And so here's a left view, and Claudia and I are looking for the right-hand view, and we find a right-hand view. Very similar, and so all we need to do is put them together, left to right, and give them to your left and right eyes, right? And we should get a nice stereo picture, right? But there's a problem. The problem is that the sun has moved between the exposures, and so the shadows are all in the wrong place, and it gives a very uncomfortable feeling. We're getting kind of a stereo, but it's not a useful image to be able to use for instinctive searches for landing sites. So the only way I know to counteract this is to map physically the shadow from one image to the other, from the left to the right or the right to the left. And it's an arduous process because you have to map it in space exactly where it falls onto a very uneven surface. But if you spend countless hours, like a geek like me is willing to do, you get rid of those shadows, discrepancies, and you get this. I could at least have had an ooh from that, but but that is what happens. So for every time that Bennu Commander Dante asked us to produce new images, this is the process we went through. So you can imagine a lot of labours of love went into this project. Okay, moving on. Stereoscopy is quite interesting for seeing objects early. This is the discovery of Bennu, and we see it because it's moved between the two exposures. Okay, it's a kind of false 3D because it's not actually in front of us because it's nearer to us. It is nearer to us because it's in front of the background stars, but it looks like it's standing out because it's moved between the exposures. But it's a very good way of discovering objects. The other way, which is often used, is the flashing technique. You know, you flash alternate pictures in front of your eyes and you see the thing moving. But this is a good way. So there's Bennu discovered, just a white dot. Along comes OSIRIS-REx with their magnificent rocket, magnificent Atlas rocket. And this is before I knew Dante, so it gives me a rather nostalgic feeling. Jumping straight in, this is the complete record of where the spacecraft went. And you can see the point where it actually dips onto Bennu and takes the sample. But now you begin to understand why we have such an amazing wealth of data from this mission, because it was there a long time and it made all sorts of passes in different directions around the object. This is a very tricky thing to do, and I take my hat off to the entire team, because this is not just a plane being driven around an object. This object is actually in orbit around an incredibly small object with an incredibly small gravitational field. So to achieve this needs the absolute finest adjustments in the navigation. An amazing feat. Quite nice to see it in stereo, I think, because you really get a feel for where it's going. This stereo was made by boss here. Dante actually did this because I got him very interested in stereo, and he delivered this to me and said, does this work as a stereo? And I went, oh yeah, my God, it does. This is as much as was known about Bennu from the ground. It's built up from radar pictures from the ground level. Where did they do this?
Arecibo Radio Telescope in Puerto Rico collected these data.
Okay, so there we're starting to get an idea of what the shape might be, but we have no idea of the actual structure. Then, a little bit before the time of arrival, we start to get pictures. This is a long way away, so it's very grainy and not very many pixels involved here, but Claudia and I are already on it, and we're producing stereos as best we can. And actually, it works, even at this small amount of resolution. You can start to see a crater there, and you can see an object hanging off the left at the bottom there, and it's all quite clear where they are in space. And we did a lot of these, and this is what we were sending to Dante and saying, look what we can do. And he got hooked.
That's right.
Makes me very happy. And then the day comes when we're actually parked beside this wondrous object and starting to get incredible images of this quality. Again, okay, this is a left-hand view, and Claudia was able to find a corresponding view which serves as the right-hand view. And I think the two views would probably be about half a mile apart, maybe. We're about a mile away from the object. Half a mile is good enough to get a good separation, a good baseline. So here's the other one. Right, left, right, and then the two together. So I'm probably driving the transmitting people mad here, sorry. There we have the stereo image. And at the bottom here, you see one of our favorite objects, Ben, the largest rock, if you can call it a rock, on the surface of Bennu. And of course, at the equator, you're beginning to see very clearly what a crater looks like on a rubble pile, or as Bennu likes to, as Dante likes to say, you know, in a ball pit. Interesting that you don't really see this nearer to the poles. And we think this is probably because the material keeps sliding down towards the equator, because this thing is spinning and the material at the equator is only just held there. So counterintuitively, if you had a ball there, it wouldn't be rolling north or south, it would be rolling towards the equator, which is a point of lower potential energy.
You can really see the difference in the craters compared to Vesta, which had sharp rims, really clear and clean. This kind of looks like a thumbprint into a sand pit, right? Which is essentially what you're looking at here.
Very nice. So this is nicely illuminated from one side, and we like that because it gives us nice shadow detail. Again, it takes a bit of work to make it work. And then illuminated from the other side, it looks like this. And again, we're seeing lovely detail in the craters there. Again, we just find ourselves poring over these images for hours looking at details. But the ship was able to... yeah, before we leave, this is interesting because you're looking at something like a full moon here, same kind of illumination as a full moon. The sun is directly behind us, so we don't get all the shadows, and we get to see the real contrast that exists on Bennu, and you see it's a lot. This thing is incredibly black. It's only about an albedo of about 3%, right, which is something like a piece of coal. It's very, very dark, but you can see that there is a lot of variation in albedo, and all these black points seem to be high up, interestingly enough. They seem to be things which are on the surface, a lot of these black pieces, and we hope we got some in the sample. Right, Dante?
That's right, and the one that's pretty prominent on the left edge of the equator there, that's the gargoyle that Brian showed us at the beginning of the presentation, and we saw it from the top down. Now you're kind of seeing it looks like a statue, which is why we named it that in the first place, just hanging off the edge. And as Brian said, if this thing were to spin any faster, that might just go flying off into the solar system.
Yeah, and if you were standing on the equator and you jumped, you would not come down.
That's right.
I'm fascinated by how black these kind of add-on rocks look, and you wouldn't really get that instinctively. It would take you a long time to discover that without the stereoscopic image. I'm always like an evangelist for stereo. I'm always pushing it, forgive me.
And some of those really bright ones are the Vesta fragments. Vesta's a much brighter asteroid than Bennu, and they shone like beacons even on the way in.
Yeah, we're going to see some of those later.
Yes.
Okay, now we can go closer, and we're getting landscapes.
We have the gargoyle again on the left edge here, towering over the surface.
Does the pointer work? No, I don't think the pointer's going to work. Okay, yeah. I'm going to spin through fairly quickly because we're not as well off for time. Again, Ben. This is Ben. Seen from a different angle, and we can go even closer. Oh no, sorry, this isn't the one. This is our rock pile. This is our landscape of boulders. What do you call that? This is called, I can't pronounce these things. Tlanua Regio?
Tlanua Regio, or more affectionately known to the team as Boulder Town.
All these features are named in Latin after, did we mention this? After mythical birds.
That's right, yeah. So the naming theme is everything is birds or bird-like creatures. And I was actually happy they got the gargoyle through, because I thought maybe that's a little bit on the edge, but they took it.
Yeah. And there we go. And regio, of course, means region. We have saxa, which means rock, and we have crater, which means crater, which we will see. So this is the only regio, right?
That's right.
The only named regio on Bennu. This is Brala and Dinewan craters. Anything to say about that, Dante?
It's the Braga is the big one. That's right there. And you can see it's really smooth around it. One of our science team members realized that all the ejecta got thrown to the north, and you can map out where it all landed, which is unusual. Usually the ejecta is such high velocity that it goes flying away on these small bodies. And then the Dinewan, it's kind of like a crater within a crater. It's kind of sitting right there in the center. And that gives you a sense of how old this one might be, because the more craters you see, the older the surface. It's kind of just a record of its exposure to the space environment.
Here we have our Ben again, getting even closer. And you can see that couldn't really happen on Earth. It wouldn't be able to be suspended in that way on Earth. It would just fall down. Here there's almost no gravity, so it can just sit there.
And it took us a while to wrap our minds around the microgravity environment. Even to the end, when we made the sample, it was that microgravity that fooled us, and why the surface responded in such an amazing, energetic way.
Going even closer and round the back, here we see some of the structure of Ben, and we see this kind of striation. And this is due to what?
That's a good question. I have a student, she's working on this right now, Kana Ishimaru, and that's, we see lamination here. We see it in the gargoyle as well. It's kind of right towards the bottom center of this image. And our preferred interpretation is this is like sedimentation, sedimentary layers on that much larger object. Remember, this is just like if you took a cue ball, smashed it into pieces, and took a little bit of it back together. That's what Bennu is. So we're kind of trying to piece together a story from a much larger object based on the fragments that randomly collapsed together to form Bennu.
Fascinating. So some rocks now. This one's Gullinkambi Saxum. Gullinkambi rock.
And again, the layers, right? Nice linear structures, very unusual. You know, this object, I believe, is maybe 20 meters across or so. And the other thing is, you know, so all of those boulders that are down at the bottom, that's what most of Bennu's surface looks like. So we're talking meter scale or larger, and our sample collector's 30 centimeters, right? And we're looking for 2 centimeter particles. Almost all of the images that we were staring at were this rugged boulderscape. Really was quite a challenge.
And the rock Huggin and Moonin Saxum.
I really love this one. We actually published this. Brian is a co-author on a science paper where we're trying to understand. I told you about those particles that were flying off into space. And I was particularly intrigued by the structures in the upper right corner there. They look like slabs that have been tilted up, maybe through some kind of thermal expansion and catastrophic failure, and it just popped up. In fact, if you look to the left of it, there's a ridge or a cliff line, and those two kind of fit together like a little puzzle piece. So this was a different contribution that Brian made to our science, trying to understand how these rocks are breaking apart and throwing material off into orbit around the asteroid. And this structure was one of our clues as to what might be happening there.
Yeah, it kind of gives you vertigo because we're near the South Pole here and we're looking down. Quite interesting perspective there. Okay, zooming in on rocks now. This is Dodo. We have a dodo here. I remember it as a kid. I used to love this place. I've got to just say, you know, I used to come here and see the dinosaurs and see that room where all the meteorites were and just be open-mouthed. I never dreamed I would be back here heralding the appearance of a pristine sample to go alongside those meteorites.
And what's really cool about Dodo is the two textures, right? The lower texture is kind of hummocky and highly fractal, and then you get to the top portion and it's much more compact, probably smaller grain size, and the boundary, again, is almost linear. We're seeing these linear contacts all over the asteroid, which is why we're interpreting them possibly as sedimentary deposits, which is really stunning compared to meteorite science. Most of my meteorite science colleagues don't believe us yet.
Yeah. Camulats Saxum. Lovely rift here, lovely fault here.
That fracture. So you can see the rocks are breaking apart. Again, maybe some kind of thermal stress. Remember, Bennu is spinning every 4.3 hours. The temperature's heating up over 400 degrees Kelvin down to maybe 250 degrees Kelvin, and that causes expansion, contraction, expansion on a very rapid time scale, and the rocks just seem to fracture and shatter under that duress.
Here we see something interesting, one of those bright particles that came from Vesta, right?
That's right. Over there on the right, we think is a fragment of that much larger asteroid, Vesta. And we're fingers crossed there's a little bit of that coming home. We're not sure because they're pretty rare. They're not common, but you can see they really stand out, and they're almost all saturated like that because they're so much brighter. You know, Brian mentioned the really low reflectance of the surface, 3 to 4%. So we built the cameras to image those dark conditions. So when you get a normal rock like Vesta, it just really saturates the pixels in that area of the image.
This is Bobri Saxum.
Yeah, this one also really shows the different structures, layered structures, and also the indication that the whole thing is just fragmenting and falling apart. And it just protrudes above the surface. All these really dark ones seem to stand out. They looked like warts when Brian sent that first stereo, the one he showed early on, which was the full disk illuminated from behind. Quite astonishing. I always call it a salt and pepper kind of texture. We got these really bright and really dark rocks mixed together. We have ideas on what that all means, but of course we're anxiously waiting the sample to help guide us in better interpretation of all these images.
Yeah. And then if you thought it was getting predictable, have a look at this. This we call Strix Saxum. And, okay, tell us where this came from.
Yeah, good question, right? This one I'm still scratching my head over. It's so smooth and rounded. When I see rocks like this on Earth, it's like sculpted by the wind or water. It takes a lot of energy to kind of smooth a rock surface. Think of rounded pebbles in your riverbeds. And we don't have any models for asteroids behaving in that manner. I think you have a flyover of this one.
We
right
do,
now.
we can fly over it. Thanks to the genius of Denis Pellerin, who I think deserves a round of applause for this. And here we go.
Yeah, this one I really, it's stunning. Very different, almost a kind of a unique structure on the surface. If we find, we'll be looking for rounded particles, evidence of mechanical weathering and abrasion to kind of smooth out surfaces like this, but really a shocker.
Yeah, that right-hand face is actually quite big. It's foreshortened, so we'll see that again in a minute.
Yeah, this is about 5 meters, this rock, in length.
This is Cinquia Saxum.
Yeah, this one to me looks like mud, right? Mud flakes, mud cracks. That flake is just pointing right off to the left there. You can see the big shadow. I'm sure Brian labored to get all of that to line up there. And it's like, what? We have mud flats now? What are we looking at here? Just really astonishing textures, unlike what we see in our meteorites, really. And again, the other thing is fun is just to kind of wander around the surface and look at all the neighbors. They're so distinct and different.
And as Dante said, a lot of this stuff probably would not make it through the atmosphere, so we've probably never seen this in our meteorite samples.
Yeah, we do know most of this is really weak. And by the way, the story about the beaches, they do heat up and cool off very quickly, like sand, even though they're giant boulders, which was really threw us for the loop. But they're very porous, and that's why they're weak, and that's why they have the thermal properties that kind of mimic fine-grained particles.
Gamayan Saxum.
Much more sturdy. You can just get a sense, fine-grained, compact. It doesn't have that kind of fractal surface texture to it. So a very different kind of rock type. And again, I love just wandering around the surface with my eyes and taking in all of the variety of materials. And especially in the upper fragment there, it kind of looks like a triangle has been cleaved out. I actually think it's probably sitting right above it to the upper left. Again, evidence that these rocks are just naturally breaking down due to the probably heating from the sun and maybe micrometeoroid impacts that regularly hit it in near Earth space.
I think it's interesting that we can linger on these so long. This is very Victorian. The Victorians loved their stereos, and they would sit and look at them for hours at home with their little stereoscopes like we're doing here, because you're in that world and you can wander around it and imagine touching these things. Okay, moving on to craters. I think we have a flyby here. Let me just see. Yes, we do.
Really shallow, really wide, very different kind of process going on here. Again, I always think of like a little kid just sticking their thumb into the sand pile and leaving the thumbprint behind. That's essentially what you see going on asteroid Bennu.
And we're starting to look at the floor of those craters to wonder if there's any place to land. Right?
That's right, yep.
It's beginning.
The big craters is where we started. They did look like they might be a little smoother, but when you get to the resolution of the sampling, they're still way too big.
This one's called Huhuk, and again we can fly.
Again, the big craters seem to be best preserved at the equator. And as Brian mentioned, because of the spinning motion, it's kind of like the tilt-a-whirl ride. Everything is just being driven to bulge out at the equator. And therefore, craters in the higher regions are erased due to the motion of material through them.
Now, Hokioi crater.
Finally, a glimmer of hope, right? When we got the stereo of this site, I was like, okay, wait a minute. This is 20 meters across. This is where Nightingale is located. And so you can get a sense from the mono image that I showed to this fine-grained region here. I'm like, okay. Now we might have an idea that we can get in there. 20-meter diameter crater loaded with meter-scale boulders inside of it. Our guidance accuracy was 50 meters. So I called up my project manager. I said, you got to redesign the flight software, which is what your project manager loves to hear when you're flying a spacecraft 100 million miles from the Earth. And I said, you got to go bullseye. We need to get right in the center of something like this. And it was these kinds of stereo images that convinced me these were where our target was going to be. That's right. It's autonomous. When we were sampling, we were over 200 million miles away, 18-minute one-way light time. So there's no joystick in the spacecraft. It has to be smart enough to make it safely, or if it decides it's too hazardous, to go ahead and back away to live to sample another day.
Yeah. I've included this one because it shows we have another weapon. We can increase our baseline even further and exaggerate the vertical dimension, which gives us an even better idea of what the terrain is like at the bottom of those craters. It's a little bit taxing on the eyes, so I won't leave it up there for too long. But you can see the use of the stereo exaggerated, hyper stereo as we call that. So we're going to skip the 50-odd images which we looked at and take you straight to the final 4, which is very exciting, of course. The first candidate is Kingfisher, which has some tight boulders, some challenges to navigation, would you say?
That's right. This was, because we needed a lot of eyes on the surface, we actually farmed this out to citizen scientists. This was their top choice. And I agree, that little patch kind of just to the bottom of the center of the image, that's the finest grain material we see on the surface. And I really wanted to get in there, but it's only a meter across. Right, so I already told the team, you got to go from 50 meters, maybe down to 10. And I was like, well, could you do 1? And they're like, no. Okay. That's just too tight of a spot to get into.
Yeah. So, candidate number 2, the Bralgar crater, which we've actually seen before, but it's a different view.
Yeah, this is on the southern wall, and what intrigued us here, and I actually thought this was going to be the site because, so we're looking down slope from the top to the bottom of the image. You can kind of get a sense that boulders are tumbling down the ridge, except there's this giant rock in the center top of the image. It's kind of shielding that material, so there was this little landing strip that was generally free of the larger hazards, and it was really flat. Even though it was pitched at an angle, since we're in microgravity, all you got to do is change your reference frame and just make sure the spacecraft comes in at 90 degrees to the surface. This was our top choice for a long time until we got some higher resolution images.
Osprey.
Yep, this is the one the engineers really liked. There's no giant boulder on the rim. There's that strict saxum that Brian showed with the smooth surface. We were looking from the right here. We called it 12 o'clock rock because it's actually pointing north. It was kind of 12 o'clock on the clock face. And we were going to have to stay away from that, but otherwise generally flat. You could see a little bit of hill motion. That was still making the spacecraft engineers concerned. But because of the lack of giant building-sized boulders, they thought this is where we should go. But the science wasn't here, right? The science was Nightingale. I knew we had to take the risk. I called the beast over there on the eastern rim Mount Doom, because we were all worried. We could say, well, we're probably going to get in there, but if we hit one of those large boulders, we're going to tip over, fire those rocket engines, and fly right into the middle of Mount Doom and mission over at that point. But I said, I had faith in the team. I said, I know you can do it. At the end of the day, they said, you're right. We're going to go for it. We're going to go for Nightingale.
There we go. Okay. A model to roughly give the scale and the feel. Mount Doom is in the background there.
Right, so the spacecraft's about the size of a van, and we had to park it in the spot about 4 parking spaces across, 200 million miles away, 18 minutes in the past. We had to make the spacecraft smart. We continued to improve its ability. It was fully autonomous and in charge of its own destiny when we gave it the command to go get the sample. Autopilot.
I don't know how you slept. I really don't. Okay, this one I really like. This is just a second before touchdown, and you've seen this in mono already. And the center of that yellow circle is the exact point of touchdown.
Yeah, so you can see it bisects the rock that got crushed, right? That's kind of at the 10 o'clock position on the clock there. So we hit it right in the middle. It just shattered like a puffball. And then the seesaw is, you can see we barely just caught the lip. I would say it's about 8 o'clock on the clock there. We just touched it, but then that whole thing flipped up and launched all the dust particles that were on top of it. So the exciting thing is, and I always tell Sarah, think about everything inside that yellow circle. It's probably on its way back to Earth right now.
Yeah, we hope. Yeah, and this is opportunism at its best, really, because there were 2 cameras we were able to discover, and they were conveniently placed for us to be able to get a stereo image out of them at this point, at this point only. So this is a simultaneous stereo, which we don't often get. Most of what I've been showing you are sequential stereos. You take one and then you wait your moment and you take another one.
Right, so that's 30 centimeters across, and still the surface is rugged and rough, and right? There's no flat areas anywhere around here, but this was as good as we got.
So this is before impact, before sampling, and this is after. So I'm going to flip backwards and forwards a little bit here. You can see there's quite a crater there around here, and you can see the material is quite dark that's been exposed. So I'm just going to go back again, before and after.
Yeah, that darkness is exciting because we think that means organics, carbon, right? When you think of dark materials, you think of carbon-rich materials. So, and that crater is about 70 centimeters deep, which is consistent with our prediction that we went 50 centimeters into the subsurface while blowing the gas through that tag sand collector.
I can show you a little movie, just zooming in here. Again, thanks to Denis for fantastic work, just so we get a clear picture of what it was like before the sample. And then after, again zooming in here, maybe you can get a feeling that is quite a deep crater there.
And we also said X marks the spot because of those 4 thrusters also dug channels. They were canted about 45 degrees to prevent getting any rocket fuel on the sample, but it carved out 2 crosswise channels on its back away as well.
So this is kind of, I'm giving you headaches now, I do apologize. But if you look at the bottom part of this, it's quite a normal stereo. The top part looks confusing because we're getting 2 different moments in time to our 2 different eyes. The one on the right is before, the one for your left eye is after. So if you squint one eye and then another, you can see there's some confusion. But the confusion actually tells you quite a lot because it tells everywhere where it's confused, that's the disruptive area. So it's disrupted quite a large area here. So I apologize for that. I'll move on before it gives you headaches. Now this is the denouement, really. This is the back off once the sample's been taken. We've seen it in mono before. We can do better because of those 2 cameras, which we so fortuitously had at our disposal. We're able to make a stereo out of it. And because they're all effectively sequences of images, we can make a very short movie of this happening. Of that.
Wow is right.
Yeah, we've all been just staring at this for long periods, zooming in on one particular particle and seeing what it does. So that's it, really. Unfortunately, that one isn't in the book.
Well, one of them is, but not the movie.
Yeah, not the movie. Yeah, the stereo is, but not the movie. Yeah, and here we are. I can contemplate this for a few hours if you like. I can leave it up there. Thank you so much. Thank you.
Have a seat. Thank you. We're going to set up very quickly for a couple of questions because I don't want to do that. While we're setting up, Sarah, we should ask about what happens next. Can you tell us what you're looking forward to doing with these samples? Let's assume they get back fine.
Of course they will, yes. Yes, so when they get back, they're going to be sent out to scientists all around the world, at 4 continents and hundreds of scientists. And the analysis of them will be coordinated by Harold Connolly, who's the mission sample scientist in the audience here. And our role will be to look, in the first instance, at a vial of dust, basically grain by grain, looking at the mineralogy and the chemistry, looking at whether we've got fragments of different asteroids or if it's all the same one. And we'll use our unique selling point of our brilliant meteorite collection. So we've got this incredible collection here that we'll use as a touchstone to compare all of these samples to. So yeah,
Fabulous.
It's going to be an exciting time. Busy times,
yeah.
And it will be all as well thanks to the brilliant meteorites team, who I hope many of you in the audience got a chance to meet as they were showing.
We'll come back to them in a sec.
Okay.
And of course, you'll come back to a future event to find out what we've found out. But let's take some questions now. Let's start with one in the room if we can. Who's got a burning question? Yeah, right next to you, just there in the front. Thank you.
Hello. Just to ask, could you have completed the Bennu mission without the images from Brian.
Great question.
That's right. Well, it's hard to predict, what ifs kind of thing. All I can say is it made a huge difference, right? It made a huge difference to us. So the team is really good at, solving problems, but, Brian was part of the team, so I wouldn't discount any of those efforts. And thank goodness that he was there and that he was willing to work so hard. I was astonished at the amount of labor that he put in. And it was, I thought at some point I was just going to break him, right? And I think he almost said that, right? I think in some of the emails. Like, if we keep this up, he's not sure he's going to be able to keep going. But
There was a point.
it's hard to say what if, but I'd say thank you very much for the contributions, and it made a big difference. And it just also uplifted the team's spirits to know that somebody like Brian was interested in what we were doing and was willing to pitch in and help.
So Dante, there's actually a related question online from Snowy who wants to know if you were doing this again or planning a new mission, would you add a stereoscopic camera to the mission?
That's a good question. I think, and I'll let Brian answer this too, but it seems like the baseline that's needed is actually so large, right? That a stereo camera doesn't really get you what you need. You need to put the spacecraft in different positions relative to the asteroid.
That's right. It wouldn't have made a huge amount of difference, strangely enough, because 99% of these stereos were obtained sequentially, and it's just because the thing is moving, or else the object is moving, or both.
Right.
If you were actually on the surface and cruising around, yes, you wanted a stereoscopic camera then.
So maybe, I mean, we kind of had one just by accident for the closure when we were close to the surface, as we saw from the backaway movers. So we might have done something to optimize the stereo characterization. We would have had the whole backaway instead of just where the frames overlap. But I think you need to just zip around the asteroid like you saw Brian showed us with the orbital diagrams there.
Yeah, worth mentioning that missions like Perseverance on Mars do have stereoscopic cameras built on the rovers.
It's easier when you've got a bigger spacecraft. Let's take another question in the room. Who has a further question? Let's take the gentleman just in the second row here.
Thank you, that was amazing. Just a question, can you remind us and put in context the dynamics of Bennu? You talk about distances, how fast it's traveling, the rotation, you said about 4 hours. Just want to get a sense of the bigger picture, as it were.
Yeah, sure. So Bennu is a near-Earth asteroid, and it's an Apollo-type asteroid, which means it actually crosses the orbit of the Earth. It gets within about 0.89 astronomical units to the Sun, with the average distance from the Earth to the Sun being 1. So it gets in about 10% closer. It gets out a little bit past 1.3, so it's an eccentric orbit, and it takes 1.2 years to orbit around the Sun. So the Earth takes 1 year, Bennu takes 1.2. Every 6 years, they do a close approach. So we discovered it in 1999, characterized it in 2005, 2011, launched in 16, did the gravity assist in 17, and we'll be back in 2023. So this kind of 6-year cadence characterizes its orbital period relative to the Earth. 500 meters in diameter, rotating every 4.3 hours. The acceleration at the surface is about 5 micro-Gs, with a G being what we're feeling right now at the surface of the Earth. So 5 millionths, kind of the same acceleration astronauts experience on the International Space Station.
Amazing.
Excellent. One last question from online, I think, an early one who came in, Brian, which is more or less, how on earth did you get into spectroscopy? How did you end up here?
Stereoscopy, well...
Stereoscopy, sorry.
It's kind of a lifetime thing, really. I got into it because of Weetabix. Because when I was a kid, eating cereal was much more exciting than it is now. You used to always get a toy in a cereal packet, and the toy that you got was this little card with a picture of a hippopotamus on. Well, actually, 2 little pictures of a hippopotamus, very flat, and you think, what the hell is this? It says, send away 1 and 6pence and a packet top, and we will send you a viewer. You put it in the viewer. I sent away, obviously. In comes the viewer. I put the card in the viewer, and suddenly I'm looking through a window at this hippopotamus, which looks completely real, and I could touch it. And I was hooked. For the rest of my life, I'm looking for stereo images everywhere. So, of course, when the missions start to go to the objects in the solar system, I'm looking, I'm thinking, where can we make stereos? And of course, you can make them everywhere because everything rotates. I mean, name me an object in the solar system or anything else that doesn't rotate. Because it rotates, you get your different viewpoints. You can put them together, make your stereo image.
it's a nice reminder that I think that inspiration can come from everywhere, even a
Especially
box of
Weetabix.
cereal. So I think that is probably all we have time for this evening. Don't forget to watch online on the 24th of September when the OSIRIS-REx capsule returns successfully to Earth. NASA will be streaming it live at 3 p.m. British summertime if you want to make your diary entries right now. All that remains to say is to give thanks to our panel, to Brian May, Lauretta, Dante, Sara Russell. Thank you, Chris. Thank you very much.
Can I just mention rather prosaically, would you please leave these on the back of your seats?
Thank you. And as the panel leave, let me remind you that if you're online or if you're going home to somewhere with the internet, you can watch tonight's discussion again and see more exclusive content on the Hive, our members and supporters area. There's lots more on there as well. If you are online, give us feedback via the chat. Thank you all for joining us in person. If you are here in the museum, the bar is still open. Sarah's team are still wandering around with meteorites. And there's a chance to get your very own 3D copy of this wonderful 3D book and have it signed by the authors. Do save the date for the 14th of September, which is our next Dig Deeper talk with National Geographic explorer Chris Rayner talking on the forefront of discovery, taking a journey into the people on the frontiers of conservation. You could book tickets now if you're a member and a supporter, but they're open to everyone from tomorrow, so be quick. Thank you for joining us. Thank you for your support of the museum. Have a great and Bennu-filled evening.